Hello and welcome. Today I'm going to be presenting on the fundamental workflow and composite design capabilities in 3DEXPERIENCE CATIA. Being an overview, the topics are presented at a high enough level to fit within the webinar time limit. However, I will be providing my email as well as setting up time aside at the end, so if you have any follow-up questions, please do not hesitate to ask during this presentation. We have a questions box as part of our interface. And also, if you want to provide follow-up questions, you can feel free to use that email, and I'll be more than happy to respond back to you. A little bit about me. My name is Tim Ramos. I'm a senior application engineer with GoEngineer, based out of Denver, Colorado. I graduated from Rensselaer Polytechnic Institute in 2014 with a degree in mechanical engineering and materials science. Afterwards, I worked with Honda R&D, designing sections of vehicle bodies. I designed sheet metal parts using advanced surface design and plastic injection molded parts using solid part design. In 2018, I transferred over to my application engineer career path and have been focusing on all things related to CATIA V5-6 and 3DEXPERIENCE CATIA ever since. Quick overview of our agenda today. I'm going to be providing some introductions. First was me, which we've already done, but I'll also be introducing the composite material, the industry challenges of designing composite parts in CAD and how CATIA combats those challenges, as well as discussing the process of your Ply and composite definition and developing your Plies in 3D with one of three approaches. So I'll jump into those approaches and discuss their use cases, where they're best used, and I'll be focusing on one approach but wrap up the other two and how they coincide with that first approach. And once we've developed our Plies in 3D, I'll talk about finalizing our design, so developing our edge apart and creating our solid and top surface. And after that, I'll be discussing different ways we can analyze or probe our data, so gathering both physical and composite definition information, exporting it, viewing it on the fly, as well as some different visualization options that we have. And finally, I'll be jumping into manufacturing preparation, so running the producibility analysis for hand layout, as well as countermeasures for issues that may arise in that producibility analysis, generating our tooling surfaces, different types of drawing creations and exports, as well as exporting laser projection for hand layout. So, introduction to the composite material. A composite material is a material that's comprised of two materials with distinct characteristics that are combined to create a superior material with enhanced characteristics. Of the two materials, one is made up of fibers and is known as the reinforcement phase, and these are embedded into a continuous material known as the matrix phase. The matrix phase accepts a load over a large area and transfers it to the reinforcement phase. The reinforcement phase carries a larger load but is anisotropic, meaning the properties are different in different directions. In this case, it carries the load along the direction of the fibers. Therefore, fiber orientation is very important in composites design, and part of the reason why designing composites is so cumbersome. Two quick examples of composite materials, one being carbon fiber, which is that fancy black weave material that you see in performance parts for performance cars, as well as the frames of road bikes that you typically see in like the Tour de France. Another example are fiberglass sheets, which boat hulls are typically made of, as well as the shells to your hot tubs. So some benefits to composites that are attractive to designers are that they provide a good high strength to lightweight ratio. They have ideal corrosion and chemical resistance. They're non-conductive, and they're durable. And some of the challenges that come with designing composites, specifically when they deal with designing in CAD, and how CATIA combats those challenges are, the first being there's a large amount of data to manage. So when compared to parts being built by solid design or surface design, there's a lot more that goes into it. So to start off, we already start with a surface as our base geometry to develop our composite definition off of. And within that composite definition, we're developing a ply, which is a sheet of composite material. And in that ply, we're defining the contour of that ply, the material associated with it, as well as the fiber direction. And then we repeat the process and define the stacking of those plies and how they stack on top of one another, known as sequences. We also have to deal with how the different sequences interact with one another and how we transition from one sequence to another. And that's just kind of the tip of the iceberg. So within CATIA, the amount of data is still large. However, CATIA does very well at handling large data. Just like with dealing with large assemblies, the large amount of data within your composite definition is also handled in CATIA very well and efficiently. For example, when you bring in data and load it in, CATIA will only load it in piecewise based off of the data that you need or want to see. Everything else is kind of just shelled representations, and the full definition is not brought in until you activate or probe that data. Talking about 3DEXPERIENCE specifically, the first time you open your data, it's pulled from the database, and subsequently, at the same time, it's building a cache file of that data. So upon subsequent openings, it's instead pulling from that cache instead of from the database, as well as when you selectively load in your data. This way, your data loads in a lot faster. The next challenge being lack of concurrent engineering. So typical CAD softwares, there's only one version of the data that somebody can check out or reserve at a time. In CATIA, they have two different types of representations for your data, one being the reference, which houses your geometry and design history, the other being the instance, which is a copy of the reference and is instantiated into an assembly and positioned. So in CATIA, one user can theoretically reserve the reference and work on the geometry, while simultaneously another designer can check out the instance and instantiate that geometry and place it simultaneously. Next challenge being no integration between analysis, manufacturing, and design. So currently in typical CAD softwares, the CAD is agnostic or not connected to your sim or manufacturing. You have to typically export that data to a neutral or a converted format and then import it to either software, run your analyses, and then report the findings back. In CATIA or 3DEXPERIENCE CATIA, all your data is interconnected. So your CAD is connected to your manufacturing, which is also connected to your simulation, and you can pull and reference and open each other data from another. Where this is also beneficial is since everything is connected, one designer can be working on the CAD and save the data, and the manufacturing or sim teams can reliably grab the most recently saved version of that data and work on it. What's more is that in simulation, currently within the composites realm, the simulation is actually what's defining the composite definition, specifically for the simulation. And after the results are run, there's no way to convert that data and push that composite definition back into the CAD. Typically, it has to be manually recorded in some way and then relayed over to the manufacturing team. The next challenge being lack of ability to predict manufacturing issues up front. The current process involves exporting your data from CAD and delivering it to the manufacturing floor, where they will test run the design and the setup and report any issues back, allowing the designers to compensate and fix those errors afterwards. In CATIA, we have a functionality known as the Producibility for hand layup, and this will predict the hand layup process and map the deformation of your fibers and check them against limits. And it will report also back the width of your roll as it lines up with your flat pattern. And it's because of these above challenges that typically designing and manufacturing your composite parts will take longer than when you're dealing with solid-based or surface-based designed parts. So looking at the process of developing our plies, how they stack up, or our sequences, and creating those plies in 3D or in our tree, there are three different approaches that we can take in CATIA to get to that point: the grid, manual, and import approaches. Now currently the grid approach is the industry standard, so we're going to run through that process using the grid approach, and then I'm going to tie in how those other two approaches get to that same point, as well as giving some use cases and some ideal scenarios for each approach. So looking at the grid approach, what it essentially is you're taking wireframes that lie on a surface, and you're intersecting those wireframes to build a grid. And in that grid, we inherently create different cells, and in each cell we define the material associated as well as the fiber direction in each cell. And then we move forward for each cell, we define a stacking where we define each layer on top of that cell where there's a material and different fiber orientation. And we do that for each cell until we have our complete definition. Then we move on to combining the cells to develop the contour of our plies, as well as subsequently defining the sequences. Where the grid approach is most ideally used is within large and complex composite parts, such as wings, fuselages, and wind blades, and also when it is necessary to consider the structure elements, such as stiffeners, stringers, and frames. So if we look in this GIF here, we have some structural elements that are intersecting with our base surface, and we're using these intersections to develop our lines that create our grid. And this is beneficial or a good best practice because we're taking the geometry that directly defines our structural or reference geometries and using them directly to build our composite definition. So in that case, if we were to move or modify any of these elements, they'll more easily propagate down to our composite definition and through to our sim as well as our manufacturing. So now I'm going to take a look at, or I'm going to go over the grid approach and specifically going through the process of defining your plies, how they stack up, and then generating them in 3D. So in CATIA, in the Composites Design app, before you can do anything at all, you need to define your composite parameters. These are essentially variables that are used throughout your design process and are consistently pulled from throughout. So it's easier to define them up front and put them in a repository instead of defining them on the fly. So here we're essentially defining three main parameters: the materials that are going to be used, the fiber directions that are going to be used, and the rosette, which is essentially a local axis system that defines your 0, 45, and 90 degree directions of your fibers in relation to your base or tooling surface. There is one more parameter known as laminates, but I'll go over that in a little bit. So the next step is to determine or import our base surface. So our base surface, also known as the support, reference, or tooling surface, essentially defines our bottom surface that we're going to be laying our plies on top of. And this can be imported from a third-party CAD in a neutral format such as STEP or IGES, or it can be designed as a typical surface in your native CAD or CATIA. The benefit of designing in CATIA is that if there are any modifications to the base geometry or base surface, those modifications will more readily push to your composite definition, your manufacturing, and your sim with little rework or error mitigation. So once we've determined our base surface, we're then ready to define our grid and grid panel on that base surface. So in this step, we're technically formally assigning our base surface as well as our rosette. Now, if we've only defined one rosette in the composite parameters, it'll just choose that one by default. But if we define more than one, then we can choose a specific one at this point. And finally, we're also formally assigning our draping direction, where the draping direction is just essentially which side of our base surface are we stacking our plies on top of. So once we've formally assigned these three factors, we're then ready to start developing our grid. And here we can see a good practice in developing our grid is taking planes and intersecting them with our base surface. And we can assume these planes are directly tied to some geometry that we're using to define our grid. So our structural elements or our reference elements. And once again, the benefit of having these directly tied to those is that any modifications that happen to those in your CAD will directly push to your composite definition. So once we've built this grid, once we've built these intersections, we intersect these lines and build our grid. Inherently, these cells are developed inside our grid. And at this point, we're taking each cell and assigning a material and fiber direction to it. And then on each specific cell, we're defining how the stack up looks for each cell. So on top of one material and fiber direction, we're assigning another different material and fiber direction. and we continue that process. So the process of having a stack up of materials in a single cell is known as a laminate. So in that composite parameters I mentioned earlier in laminates, we can define a single pattern of stacking of materials or sheets of plies for a single cell. So instead of defining each cell one layer by layer, we can just give it a laminate from that composite parameters. So once we've defined all of our cells and all the stackups of those cells, we're ready to move on to our virtual stacking tool. This tool is essentially the preliminary step to developing our plies in 3D in our tree. So in this step, we're taking all those cells that we developed and combining them together to develop our contour of our plies. And subsequently, at the same time while we're doing that, or simultaneously, we're also developing our sequence, which is essentially our stack up of our plies, where the sequence is going to be the stack up of plies that go up to the same thickness. So if we imagine two stacks of plies that are next to each other that are the same thickness, they'd be a part of the same sequence. And if we imagined a third stack of plies that were either thinner or thicker than the first two, they would be a part of their own sequence. And in this tool, we can also add, remove, and modify plies and sequences. So it doubles as an editing tool to modify our definition and regenerate our plies. So once we've developed our ply contour, our sequences, and our virtual stacking, then we're ready to move to the step where we generate our plies in 3D using plies from virtual stacking. In this tool, we have three different algorithms that we can use to generate our plies. The first being minimal crossing, which will reduce the overlap of our plies, but may result in more material overall and result also in a higher weight. The next option, the opposite, is going to be weight saving. So here we have less material used, but this may come at a performance cost. So if you don't have a design intent to go one way or the other, we can choose the happy medium, which is minimal crossing and weight saving. And finally, in this step, we have the option to create an overlay in our tree on the plies that are generated using the grid approach. So we'll have just a little icon that sits over the plies within the tree, and it just denotes we've made this using the grid approach. And I mention this because we can use the other approaches within the same part. You're not just constrained to one approach. So it may be beneficial to denote which ones are used using which approaches. So speaking of the other approaches, now we're at the point where we have developed our plies in 3D. And so we're at the point where the other approaches kind of come together, and now we're along one single approach. There's no other methods at this point. So now discussing the other approaches, I'll first go into the manual approach. This is essentially the brute force method of developing your plies and your stacking. So in this method, we take the wireframes that are on our surfaces, typically made of intersections once again. But instead of developing a grid in our cells and so on and so forth, we're using those wireframes to first develop the contour of our plies. Once we've developed the contour, then we assign a material and a fiber direction. And then we repeat that process for the next subsequent plies that we're using on that part. So this approach is beneficial when used for simple composite parts that have a minimal amount of plies, so minimal that it's actually faster to use the manual approach than it would be to create a grid, create the cells, combine the cells, etc. This is also beneficial for conceptual phase parts. The way that we're designing these plies and creating this composite definition, we have a lot more freedom to mess around with the definition and contour of our plies. And finally, this is beneficial for parts using cores, where a core is a non-composite material embedded into our composite layers to provide a certain property to our part. Now the reason that it's beneficial for using cores is just the way that CATIA is set up. So when I mentioned earlier that your stacks of plies build sequences, there's another step to it. Sequences that belong to the same domain are part of the same group. So in this case with a core, we have two different domains that we're dealing with. So we have the plies that are underneath the core, and then we have the plies that are above the core. And these are two separate domains. So it's just easier to simply create a new domain on the fly using the manual approach than it is doing the grid or import approach. So that's why I mentioned in the slide before that it may be beneficial to use two different approaches in one part. So there might be an opportunity where you want to use the grid approach but also want it to incorporate a core in your composite definition. And then the final approach is going to be the Excel import approach. And what we do with this approach is we start off with a base surface. We define the limits of our grid. So in this case, we're still building a grid. We're still creating cells and defining our composite definition that way. But we're only defining the outside limits of our grid and our base surface, because everything else, our cells, our sequences, our materials, our fiber directions, they're all going to be embedded within an Excel table. And the way that we get this Excel table is we are exporting it from a legacy part that has a composite definition already. So what this approach is ideally used for is when we're building a part that we're trying to emulate a legacy or production part that has a proven composites definition. So we export that composite definition to a table. We add in a few columns that define our starting end plane, our left and right limits, and the offsets between those limits where we're going to grab intersections for our grid. And then within this Excel table, we're also, defining those cells, defining how they stack up, defining the sequences, the materials, the fiber directions, etc. And as soon as we import that Excel doc, it'll generate all the rest of those parameters for us. So once we've developed our plies in 3D and in our tree, we're ready to jump to the step of finalizing our design. And that is in the sense of developing our edge of part and creating our solids and top surfaces. So the edge of part, it's pretty straightforward. It defines the boundary of your part. There's two different types of edge of parts. There's your engineering edge of part, which is the ideal precise edge of the part as designed by the engineer and as it's represented in CAD. And then there's the manufacturing edge of part, which is the real life representation of the boundary while taking into account tolerances and different tools. Now there's a process within CATIA that offers you the ability to take your engineering edge apart and extend it to your manufacturing edge apart so that you can take into consideration manufacturing constraints within the design phase. Developing your solid and top surfaces. Your solid, it's typically used for checking for irregularities or voids, and also provides realistic representations for presentations or renderings, and also can be used for some light FEA analysis, where the top surface is typically used to provide a reference for defining the orientation and stacking sequence of the composite plies. Now the process to build these, we start with developing an ISO thickness area, and what we do in this step is we take all the areas that are a common thickness and combine them into a singular shape, and then we move on to creating the junction lines, which will take the corners of our ISO thickness areas and build a line in between them, and this will define the transition between one thickness and another. And once we have both of these defined, then we use the final tool to develop our solids and top surfaces. So next I'll be jumping into analyzing or probing your data, so grabbing your composite or physical properties and either viewing them on the fly or exporting them to a table, as well as looking at some different visualization options. So the first probing tool is your numerical analysis. This is what's going to grab your physical information about your part, so your area, mass, volume, and center of gravity. And here we see we're grabbing this information for our plies, the sequences those plies belong to, the group those sequences belong to, as well as our material and fiber orientation. And we have here the ability to export this out to a table-friendly format. Next, we have the ability to grab core samples. This gets us our ply information or our composites information at a specific point or multiple points simultaneously in space. The nice thing about this is we can specifically set coordinates to these points so we know exactly where we're getting this data from. And some of the information that we get from this tool is of a single ply. We get the ply name, the sequence it belongs to, the group the sequence belongs to, the associated material, fiber direction, and rosette. And at a point we can get between the point of the top surface and the tooling surface, we can get the number of plies and the total thickness at that point as well. Some visualization options. We can develop a section cut where we choose a specific ply or a specific plane in our 3D and cut a section at that plane. And then we have the ability to scale that section of our ply definition and view it a lot easier in 3D and call it out to somebody that we're trying to make notes on or do a design review on, etc. And we have different visualization options available to us as we see down here. Our next visualization tool, the Ply Exploder. Similar to our section cut, we can scale our plies here, but we can also create an offset in between each ply. And we're also, instead of just doing it on a section, we're doing it to our entire ply definition. The nice benefit of this tool is we can toggle its visualization directly from our tree. And then we have a secondary tool where we can cut a dynamic section, and that'll allow us to cut a section on our part and drag it along our part and also reorient it in any way we want, so we can kind of get a custom section anywhere. Finally is our on-the-fly information. So what this is going to do is this is going to turn your cursor into a probing tool and allow you to filter between specific types of data that you want to hover over and get pop-up information on. So here we're hovering over a specific ply. This one's likely a ply from this cross section, so you can grab it from the part or from the cross section, and it'll display specific information. So here we're displaying pretty much everything. So we have the ply name, the sequence it belongs to, the material associated, and the fiber direction. And then finally, we're going to jump into manufacturing preparation. So here we're going to look at the producibility for hand layup, so looking for manufacturability issues as well as compensating for them, generating our tooling surface, creating our flat patterns, previewing our entities and importing and exporting, and building our engineering or composites drawing, building our manufacturing or ply book drawings, and then exporting to laser projection. So the hand layup process, also known as dry layup, is the process where we're taking dry reinforcement layers, or our fibers, and laying down each ply one by one, and then as a secondary operation, applying our resin or our matrix phase. And what the producibility for hand layup does is that it will simulate this process and check for fiber deformation along this process, as well as checking to ensure that our roll width can work with our flat pattern or can cover our entire flat pattern. So we can choose various factors to optimize this as well as tweak it. And that some of these factors include seed point, which is going to be the first point of contact when we're laying down our plies. So if we see in this GIF right here, we see this mesh is building from this center out, and that's showing us that that center is our seed point. We can also determine mesh resolution. So here, this blue feature, this is our mesh, and the way that it's working is that at every intersection of the mesh, it's checking the deformation of your fibers. So if we have a tighter mesh, we're going to get a higher resolution in our results, but the simulation is going to take longer. If we have a larger mesh, we have lower resolution, but our simulation is running faster. For thickness update, we can account for the thickness increasing as we lay down each ply. So this is beneficial, especially if our plies are running over a corner and creating a radius. So if you imagine over that radius, as we lay each subsequent ply on top of it, that radius is growing, so that deformation is changing on each subsequent layer. And the same thing with this, we can toggle whether to consider that thickness or not and toggling it off will give us a lower fidelity on our simulation, and having it will have a higher fidelity, but it'll take longer for the simulation to run. And here we can see in the results we have a few different features here, a few different results that we're seeing. So here we see this blue mesh. The blue mesh means that the deformation of the plies has not exceeded our angular limit that we've set. Here we see some yellow mesh. It's still in the realm of being okay by spec, but it's kind of getting to that breaking point. It's kind of a checking limit to, keep an eye on it. Whereas the red is in a failure zone and we need to compensate for that failure. So looking at some of the failures, the first one being that deformation going too high. One compensation for it is creating a dart, or essentially a relief cut. And there's two different darts that we can create: a line dart, which is just defined between 2 points, or a curve dart, which is defined as a curve on our surface. The other error that we can run into is when our flat pattern exceeds our roll width. So here we can see in this image down here, we see this yellow piece, or rather this blue piece is our part, as it is in 3D or in manufacturing. And here, this yellow part is our flat pattern. And then we see these red lines. These are denoting the width of our roll. So here we're seeing that we have to roll out our fibers, cut it, roll it again, cut it and splice it, and then repeat that process until we fit our entire flat pattern. So in this case, the producibility is showing that our roll is not going to work for this flat pattern with just one pass, and we need to cut and splice it. So we have the option to create different types of splices, one being a multi-splice, which will allow for overlap, a butt splice, which will not allow for overlap, and a no splice zone, which doesn't allow for splices at all. Next, we generate our inner mold line, or our tooling surface. So this is the surface that we generate that's going to be used to cut our tool. Now I know at first glance this does look a lot like our top surface and solid. However, the big difference between those and why those are used for their reasons and this is used for the tool is because the solid and top surface, with the transition between the plies, it's represented as these 90-degree steps here. And this is not ideal for cutting your tool and creating a tool out of. So what the inner mold line tool does is it takes those steps and allows you to create a nice smooth transition and develop a surface that is much more NC code friendly. We have the ability to preview our data here, and as well as our flat pattern simultaneously. So here we see our ply as it lies on our finished part, and next to it we see the flat pattern of that ply, as well as some color-coded options here that tell us different information on the part. And then here on top of that we can also develop our entire flat pattern, as well as grab all of our composite definitions and export them to IGES, DXF, or XML, depending on which format is relevant for which kind of data you're trying to export. And a quick note here, you have the ability to import full composite definition from CATIA v5-6. So if you have legacy data of composites on v5-6, depending on the release year, 3DEXPERIENCE has a feature what's known as mapping tables that allows you to bring in the full definition from CATIA v5-6. So technically, or typically, when you bring in data from another software into CAD, you're only left with just dead data that you can't modify the history. With this, we can take data from v5, bring it into 3DEXPERIENCE, fully update or modify the history, as well as integrate it with the rest of our project. We have the ability to develop our composite or engineering drawings. So here we see a B pillar, and we see all the plies as they lay onto that B pillar and calling out which plies are which. We also have a ply table that once again denotes the composite definition. So our plies, sequences, the material and fiber orientation, as well as our numerical analysis, which once again gives us all of our physical properties of each ply. So your mass, volume, area, and center of gravity. And then our manufacturing drawings are our ply books. So with this, we're allowed to take, or we have the ability to take each ply or sequence and give it its own drawing sheet. So here we see different views of different plies and how they are oriented on the final part. And this is ideal for developing manufacturing instructions or standard operating procedures. And finally, we can export to .ply or .cal, which are extensions that are compatible with Vertec, which is a brand of composite laser projection systems. And what this does, or what Vertec does, is it projects down the contour of each ply as it lays within the tool. So during the hand layup process, the person that's laying up all these plies can just line up the ply with this outline and thus expedite the hand layup process. And that's all I have while still allowing some time for some questions. So if there are any questions, feel free to ask them in the questions box now, or my email is provided here, and you're more than welcome to email me with any follow-up questions.